Good now.
Okay, I'm ready.
Recording is in process, so we can begin.
I am not hearing anything. Is everything okay?
Right.
Are you getting me now?
Okay.
Okay, yeah.
Okay, I'm sorry.
For some time I
Okay.
thought I lost it.
So good now?
Yeah, we're good.
Okay. Let's introduce our second speaker for today's presentation, and he is Mr. Ghanshyam Khanal. Mr. Khanal did his undergraduate from PN campus, Tribhuvan University in 2009, and then masters in physics from Central Department of Physics in 2011. And then he was a visiting student research scholar in Department of Chemistry in Princeton University. And then he joined Rutgers University as a PhD student in fall 2014. And his research area is mainly related to strongly correlated electron systems, including iron-based superconductors, high-pressure phases of iron compounds, and correlation-driven metal insulator transition, and so on. And today's title for his talk is Beyond the First Principles Methods for Lattice Dynamics of Correlated Electron Systems. Okay, so let's welcome Mr. Khanal. So, Mr. Khanal, microphone is yours now. Go ahead, please.
All right. Thank you so much, Siadai. Thank you also to Sri Bhatrai and the entire ANPA team for giving me this wonderful opportunity to present my work. And so, thank you all for coming. So today I'm going to talk about my recent research works on iron-based superconductors, and this work is recently submitted to physical review letter. And so the title of the talk is Beyond First Principle Methods for Calculation of Lattice Dynamics of Correlated Materials. And so here is the outline. I'm going to introduce the lattice dynamics. What do I really mean by that? And how do the electronic correlation effects affects the atomic vibrations or the phonons? And I'll also discuss about local magnetic moment and how important it is for these real materials. And I will introduce the standard density functional theory and talk about why do they work and why not in certain cases. And then I will finally talk about dynamical mean field theory, which improves the results significantly. All right, so this is solid state physics 101. So I think all of us know about it, but since this is a colloquium talk, I thought I should just give some basic overview. And so here I am showing you a 1D atomic chain. This is a solid with a linear chain with one type of, single atom, and is spaced with a certain distance a. And we can write the potential energy for that system by very simple potential energy, basically half x square, right? The potential energy, which can be, which then we use to calculate the forces on each atom by taking the derivative of that potential energy with respect to the position of each atoms. And if we use a plane wave ansatz, then we can write a dispersion relation, which looks like this, and we can plot the dispersion relation. On the bottom left corner, you can see a sinusoidal wave for the dispersion relation. On the bottom right corner, you can see the same similar dispersion relation. For this time, it's a diatomic chain. It's still a 1D chain, linear chain, but two different identical atoms. And one major difference that we see between these two plots is that we see two separate phonon modes, the so-called optical and the acoustic phonon modes. And there is a gap on the zone boundary, which is basically explained by the Bragg's law. And okay, here I am going to show you some of the cartoons for these two separate linear chain cases. The first one, the upper one, is for monoatomic linear chain, and the one in the bottom is for the diatomic case. And this is what is happening here is the phonons, the atomic atoms in the linear chain are vibrating up and down. And if you see in the top GIF image, you can see there is a wave which propagates, right, as the atoms are moving up and down, vibrating from their mean position. And this is also called aliasing in solid-state physics. I think we all know about it. And what we can observe here is that the two waves, the one with the longer wavelength and the one with the shorter wavelength, match at this specific atomic position, and A, right, and times A. So if you see closely, whenever we have the axis X is N times A, then the two waves match perfectly. In between the two, they do not match. Okay. So this is very basic introduction to phonons, and these elementary excitations which we get out of this sort of vibration, this classical mode of vibrations, are called phonon modes. Okay, so next let's talk about what are the standard practices for real materials, real systems. On the top right, you can see iron selenide, which is one of the iron-based superconductors, and this is the C-axis view. And what happens in real materials is real systems are far more complicated than the 1D linear chain that I just described. And the systems are described by writing the Hamiltonian, the ab initio Hamiltonian, which you can see here. The first term is basically the single particle term, where the first one is the kinetic energy, and then V external is the external potential. And the second term is the electron-electron interactions between each of the electrons present in the system. Okay, and so one of the most important theorems to calculate lattice dynamics or phonon frequencies in this sort of systems is called Hellman-Feynman theorem, which I think we all know in quantum mechanics, which basically says that the expectation value of the derivative of the expectation value of energy, total energy with respect to some parameter lambda, is equal to the expectation value of the derivative of the Hamiltonian del H over del lambda, which is basically we calculate the expectation value. And so this model is used to calculate, once we have the total energy, then we can calculate the derivative of the total energy with respect to lambda, in this case atomic position, to calculate the force on each atoms due to other atoms. And once we have the forces on each atoms, then that using this third equation, we can calculate the force constant, which is again the derivative of the force, the integration of the force around this circle of basically the vibration, the displacement of each atom, alpha. And given that, we can calculate the dynamical matrix, which we solved to calculate the phonon frequencies. I'm sorry for all the maths, all the equations, but I thought these are important, and these are easy to understand as well. There are a lot of success stories in conventional density functional theory based calculations, and here is one of them. As you can see, the phonon dispersion relations are calculated for this atom which is system which is FCC lattice, and you can see a perfect agreement with the density functional theory based calculations, and you can see the dots are perfectly on top of the solid line. However, okay, before going to the however part, let me tell you more about where do the conventional density functional based theories succeed. And this density functional theory is one of the theories which is extensively used in modern day condensed matter physics, in biophysics, in a different variety of fields. And some of the reasons are it's computationally cheap, and total energy calculations and forces are really great for a lot of materials, not all of them, but a lot of materials. And it works extremely well for electronic systems with weak electron-electron interactions, as well as molecular systems. And in the top right, you can see this bar diagram of the number of papers used, number of publications which used density functional theory as their underlying method. And you can see this graph basically is going up like exponentially. And I think I have it only for until 2016 or 17, and we can expect it to grow even more in recent years. However, this method, which is remarkably successful in a lot of systems, fails to explain a lot of rich physics which happen in so-called strongly correlated electron systems. So these are the systems in which the electron-electron interactions are extremely important, or the energy scale at which the electron-electron interaction occurs is of the same order of the kinetic energy of the system. So DFT, what DFT does is DFT basically treats this electron-electron interaction part as a single particle interaction. It sort of makes an approximation, Gilliam model approximation, which reduces this two particle interaction. Let me show you the Hamiltonian in the second part, this 1 over Ri minus Rj, the Coulomb interaction part, effectively by one particle term, and that does not always captures the rich physics that comes up because of these electron-electron interactions. For example, it fails to explain the Mott metal insulator transition. For a lot of correlated insulators, the DFT gap, predicts them to be metal, and even if for some systems where it predicts them to be insulator, the gap is not correctly explained. And it also fails in the case where the system has local moments which are basically fluctuating a lot. And here are two figures. On the bottom right, you can see two plots, electronic density of states for nickel oxide. This was predicted to be a Mott insulator, like back in 1940s. Neil Mott, who actually worked on this a lot, and after his name, this transition is basically named Mott metal insulator transition. And so this nickel oxide has a gap of around 4.3 eV, but if we do plain density functional theory, the local density approximation, this predicts this system to be a metallic system. So this is a big failure of density functional theory. Another thing that I would like to mention here is on the bottom left, I am showing the phonon density of state of iron selenide. I'm going to talk extensively on this later on, but you can see that the density functional theory peak is really far away to the experimental peak. And one thing, so why does, as I mentioned, why does the DFT fail? The reason is it doesn't capture the correlation effects correctly, and it doesn't capture the spin fluctuations, the local moments correctly. Okay, and so what can we do to go next to capture these correlation effects and these local magnetic moments? And the theory that does both of these is called dynamical mean field theory. What it does is it not just captures, it calculates the total, the electron-electron interaction system by mapping solid into so-called Anderson impurity model, where the local moments, the atom with the local moment, for example, iron or copper or nickel, these atoms are mapped like an impurity in a system where there are a lot of weakly correlated electrons, and this solves this Anderson impurity model exactly by using some quantum Monte Carlo method, or it can be any other solver, and it calculates the Green's function, which then gives us a lot of information about the system. It treats the dynamical fluctuations of the electrons in non-perturbative way. It's extremely successful in explaining the complex physics when correlations are strong, and this is the area where the conventional density functional theory fails a lot. For example, so-called Horn's metal mode metal insulator transition, high tissue superconductors, charge transfer insulators, and correlated insulators. These all are the systems for which the density functional theory does not explain pretty well compared to, and DMFT does extremely good job in explaining the physics here. Okay, so here are the two figures. On the top right figure, I'm showing this mass enhancement of different orbitals in a lot of iron-based superconductors, starting from FeTe to Ca, Fe2S2, all the way to LaFePO. All of these are superconductors. They have different critical temperatures. And so this mass, this effective mass, because of the electron-electron correlation, the spin fluctuations on each orbital is different, and the atoms become extremely slow because of the electron-electron interaction, and which basically raises or enhances this effective mass of these orbitals, these electrons in different orbitals. And here we can see a very good success story of dynamical mean field theory, where the dynamical mean field theory predictions are almost exactly on top of the experimentally measured the mass enhancement effective mass factors. And that bottom right figure, I'm showing this plot for resistivity for, if I remember correctly, this is for LaFeSO system, which is also a iron-based superconductor. And you can see this plot is shown to show that whenever we used this non-zero value of Horn's coupling, which is another term which arises when you treat the electron-electron interaction correctly, then we get this non-zero value of the resistivity. If you see the the red curve is all zero when the J-Hunt is zero, and whenever J-Hunt is non-zero, the curve goes higher up, and it basically comes down to zero for very low temperature. Another thing that I would like to mention here is back in 2017, there is a paper which was published in Science, an experimental paper, which did this femtosecond electron phonon lock-in experiment using photoemission and X-ray, and they confirmed. So I'm showing you this table in which we are showing for iron selenide, they measured this one particular phonon frequency, A1G of this particular mode A1G, and this is the DFT has predicted around 6.5, and DMFT, which predicted it in 2014, much before the experiment came, to be 5.7, and that was later confirmed in 2017 by this Science paper, this experiment. And this is one of the remarkable success stories of density dynamical mean field theory especially for the lattice dynamics and the phonons. All right, so let's move on to what we actually do in dynamical mean field theory to calculate the phonons and the lattice dynamics. Here I am talking about the Chalcogen-Hite. The Chalcogen-Hites are these atoms with active p orbitals, in this case the selenium or tellurium. And we can see these iron-based superconductors are layered materials where we have iron layer. These red atoms are the iron atom. We have a layer of iron, and the selenium or the chalcogen is just above the layer and below the layer. Okay, and that basically repeats along the C axis. And for a lot of these systems, the crystallographic position for the chalcogen or the pnictogen is 1/4, Z. I'm sorry, there's a typo here. It's 1/4, 1/4, Z. And that Z is predicted by density functional theory, which is to a very small value compared to the experiment. And that is, as we know, because of the overbinding effect which we can see in density functional theory, and also because the electron correlations are not taken correctly. And this one particular parameter, this Chalcogen-Hite or the internal parameter, is extremely important in these iron-based superconductors. And here I'm showing one figure by this paper where they have plotted the critical temperature with the anion height, which is the Chalcogen-Hite that I'm talking about. And you can see as we go towards the right, the superconducting critical temperature increases significantly even by a very smaller change in the height. Okay, so it's extremely important to have correct Chalkozin height inside your theory if you want to do calculate the correct physics or the lattice dynamics. One important thing to that these Chalkozin atoms are predicates really low intensity functional theory is because of the electron correlation, which is absent there. And whenever we calculate the electron correlations, take that correctly in dynamical mean field theory, the atoms basically are moved up, shift up, which is very close to the experimental value. Here I'm showing the plot on the bottom right. And so I have put the LGA results as yellow, PB, the GGA results as blue, and the dynamical mean field theory results as a green dot, and the experimental are the squares. And as you can see, I have done it for 3 different systems, but I have also done it for, I've shown you for 3 different systems, but I have done it for significantly other, many other iron superconductors. And for all of them, the same message that we get is the dynamic mean field theory prediction for the Chalkozin height or the internal parameter is almost exactly on top of the experimental value, which is extremely important for a lot of systems. I want to move a little faster. Now here I'm showing the phonon dispersion of iron selenide, and the black dot are the experimental dot by inelastic X-ray scattering, and we can see dynamical mean field theory phonon bands match very good with the or excellent agreement with the experiment. And on the right, I have shown you the iron and the selenium projected partial density of state. One important thing here to notice is this pink star, which is the science paper that I mentioned earlier, differs to the this other inelastic X-ray scattering by a little bit around the gamma point value. In our result, our calculations agrees perfectly well for this science paper and for a lot of other bands, which allows us to assign the different characters perfectly as I have put here. The lowest band for the gamma point is easy, assign easy character, and so on by going like A1G, B1G, EU, EG, and A2U. On the bottom right, I have shown you a table for the gamma point phonon frequencies for all the modes. And once again, as I mentioned, the dynamical mean field theory results are extremely close to the experimental results. And particularly this A1G value, the second row, 22.5, which is very close to 21.9, the experiment, and that's the science paper that explained this. And similarly for other modes, whenever we have the experimental value available, the dynamical mean field theory results are extremely close. And so you may ask, how does it compare to the DFT values, DFT results? And so here I am plotting the dynamical mean field theory results with the density functional theory calculations using the general gradient approximation. And one quick thing that we can notice here is not all the phonon modes, all the phonon branches shifts by the same amount. A lot of course, we can obviously see that a lot of all the optical modes are shifted to higher energy, and some are shifted as high as 8 MeV compared to dynamical mean field theory results. So since I already shown you in the previous slide that the dynamical mean field theory agrees very well with the experiment, so the DFT based results is different as up to 8 MeV with the experiment. And one of the reasons that dynamical mean field theory corrects is that we know that we have included the fluctuating moments, which is present because of the iron atom, and that softens the high energy phonon modes, and which now brings down to the same value as the experiment gives. And because our match with the phonon dispersion is so good with the experiment, we can now assign different phonon modes for each of the character, and that I have shown you in the bottom right plot by showing that this density of state plot. And one remarkably success story is that this dip around 22 MeV, where I have made a circle, this ellipse there, around the A1G mode, there is this peak observed in this iron partial density state observed in experiment, and dynamic element field theory has exactly predicted the dip. That's a very small thing, but this shows how sensitive this theory is to small details, especially when it comes to fluctuating moment in this local moment regime compared to the density functional theory. And you can see the density functional theory does not have that peak, and it's way bigger compared to the experimental values. I would like to move on to another system that I have worked on, iron telluride. We are preparing a manuscript for this system now. Hopefully we'll submit it soon. And as you can see, we have I've put different colors for this band. So the colors represent different atomic characters on those particular band are basically the fluctuations. And you can see we have only 3 dots which are available from experiment. The pink dots which match extremely well with the dynamic element field theory predictions or results, I should say. One key difference between the previous phonon dispersion that I showed you, FESE and FET, is these 2 bands which basically are termed as B1G and EU mode. They switch positions. In the FESE, B1G is lower than EU mode, and FETE, B1G goes higher up compared to EU. And we can explain this in terms of the atomic mass of tellurium. And because tellurium is heavier compared to selenium, and tellurium is slightly higher compared to selenium when it comes to crystallographic positions, and that makes the electron correlations even bigger in the system compared to FESE, and that's why this pushes the B1G phonon mode, which is basically the iron oscillation, the iron atom oscillations along the Z direction. If you remember one of my first slides, when the atoms are oscillating in one direction. So this B1G mode is the iron atom oscillating in G direction, and that shifts higher than EU mode. And here, once again, I have assigned different the characters for different peaks in the density state. Unfortunately, we don't have any experimental results to compare here. But the story is like the phonon dispersion relation, because the from the phonon dispersion relation we can correctly assign these peaks to different phonon modes because by looking into where the eigenvectors of these each phonon modes are, eigenvectors of the dynamical matrix that I defined earlier. Here I have shown the density of state for compare the density of state calculated using DFT and dynamic element field theory, and we can see the dynamic element field theory softens the phonon density of state, and as I explained earlier, that's because of the electron correlations present in the system. And one key thing that happens when you calculate DMFT is that the gap which appears in density function theory calculations is completely gone away in DMFT. And that's a very important thing because, as I mentioned earlier, at the atomic position of this tellurium atom and the magnetic, the local magnetic moment on iron atom, that makes it extremely fragile to these local correlation effects, and which makes this gap go away in dynamic element field theory calculations. There is a typo there, and once again, now I would like to show you this phonon dispersion relation calculated within DMFT and DFT, and the similar story as iron telluride is follows here. The dynamic element field theory plots are significant, like softer, which are of smaller frequencies compared to density functional theory calculations. And on the bottom left table, I have put the experimental values with the DFT and DMFT results whenever possible. And once again, the DMFT values for those are almost exactly equal to the experimental results compared to dynamical mean field theory. And if you look at this particular EU phonon mode, which the experiment has predicted to be 24.3, and the DFT predicts it to be almost 30.37, which is almost 7 MeV higher than the experimental value, and Dmft predicts it to a very close value to 24.3, which is 23.97. And so similar story goes with the B1G phonon mode, and these are the only 3 frequencies that we have available right now, the experimental frequencies. One important thing that I would like to address before ending my talk is the static or fluctuating moment. A lot of calculations have used magnetic DFT. A lot of people actually do use magnetic moments, static magnetic moment in traditional density functional theory calculations, which actually significantly improves the crystalline structure of the system. And as you can see in this table, I have put the results of plain DFT and plain DFT, the different functional PBE and magnetic DFT, which is LDA plus U, where we basically use static magnetic order, or the atoms are ordered magnetically with a given magnetic origin. And I have put the experimental and the dynamical mean field theory results. And for, as you can see, for both iron selenide and iron telluride, the LDA gives the smallest value, and the PBE, which is the generalized gradient approximation, this improves that a little bit. And when you use magnetic DFT, that once again improves the crystal structure by a little bit. However, even within the magnetic moment regime, the calculations are still far away from the experimental value. And you can see that the dynamical mean field theory results are much closer to the experimental value. So that arises the question that are static movement that successful, or do we actually need to calculate the, actually need to use the fluctuating moment in the system? And one second here, okay, here actually the spin phonons enhance the electron phonon coupling in iron tellurium compared to iron selenium. Here in this bottom right figure, you can see I've shown you, these are not my results, these are from these 2 papers. As you can see, including the stripe antiferromagnetic moment in the iron atom, that reduces these phonon modes, as we have seen with dynamical mean field theory. However, the magnetic moment used in the density functional theory calculations does not reproduce the Fermi surface, which is very different from the experiment. So in a sense, magnetic moment does improve the DFT results, but it does not improve all the DFT results. It only improves some of the results. And that's where dynamical mean field theory is extremely successful in both the Fermi surface as well as the local moment regime, as well as the lattice dynamics of the system. That's my talk, and here is the summary slide. I think I have convinced you that dynamical mean field theory in combination of DFT predicts external and internal parameter, as well as the phonon dispersion relation and the phonon density of state compared to the density functional theory. And I have also mentioned towards the end that the fluctuating local magnetic moments are extremely important in the lattice dynamics. We cannot just use the magnetic dynamic density functional theory to correctly calculate the phonon dispersion relations. And I would like to thank my advisor, Christian Howley, my collaborators, the postdocs and the other grad students, Lucien Pasquet, Chang Han, and Subhasis Mandal. And I'd like to also thank NSF for the support, and thank you all for coming and attending my talk. Thank you so much.
Thank you, Ghanshyam, for nice presentation. So we would like to move towards our Q&A session. So first of all, I see a comment or some link from Sambhu Ghimire sir. He has shared some link. Maybe that might be something related to Mr. Khanal's talk. So that would be, I think, helpful for all of us who is interested on that area.
Sure,
and we have a question
I'll see you later.
Question from Bishwas Lal Sresth, and he's asking, how does DMFT compares to the DFT in terms of computational time?
Oh, okay. That's a very good question, Vishwas. It is, I mean, said to be expensive in compared to DFT, yes, for smaller systems. But however, for heavier system, in fact, DFT is computationally more expensive than DMFT. I can give you an example of the two systems that I talked about, iron selenide. If you do single unit cell calculations, DFT is, of course, significantly faster than DMFT. However, if you do supercell calculations, which was needed in order to do these phonon calculations, I did 2 by 2 by 2 supercell, so which already had 8 times 4, 32 atoms in the system. And that basically fares more or less in the same level as the DFT when it comes to the calculations. So it depends on the system size. For a smaller system size, DFT is faster and cheaper, as I mentioned earlier in the talk. But for bigger system size, DMFT is not that much expensive compared to density functional theory. But that's a very good question. Thanks.
Thank you. We have another question from GD. He's asking, how heavy is the computational using DMFT compared to DFT? Can you use DMFT for non-correlated system?
Okay, that's a good question. I think the first part of that question is already answered. And the answer to the second question, that can you use it for weakly correlated systems? Yes, you can use it for weakly correlated systems, but I don't see any reason why you should do that, because if the system is not strongly correlated, then DFT does extremely good job there. So as I mentioned earlier, DMFT, which is slightly more expensive than DFT results, and I don't think we should use DMFT for weakly correlated systems, although it is perfectly okay to use this method for weakly correlated systems as well. And it has done significantly well for the weakly correlated systems. Yeah.
Thank you. We have another question from Dr. Sambhu Ghimiri. He's asking, what about the band structure of different phases, such as metal insulator phase?
Okay, so I didn't have time to actually, initially my plan was to talk about these iron-based compounds, high pressure phase of iron-based compounds. And we have done some work on band structure for this different phase. In particular, I have worked on iron-based compounds for high pressure, and that band structure, the band structure has been really good for DMFT, and even for other iron-based superconductors. I haven't worked myself, but I can show you the links where the dynamical mean field theory prediction has been extremely successful compared to DFT results. I think, yeah, that's that much I can say. And including iron selenide, there is a paper by Christian in 2014, Christian, my advisor, in 2014, in which they calculated the band electronic band structure, including the Chalcosin height and the different mass enhancements for different orbitals for iron selenide, iron telluride, and all the other systems, and it has been extremely very close to the experimentally measured band structure.
Thank you. I don't see any more questions in chat box, so everyone please, I got one from Dinesh. He's asking, have you ever used sulfur as chalcogen?
That's a good, that's a good question, Dinesh. I have done some calculations for FES as well, which is in the same category as FESC and FET in terms of the crystalline structure. This is the same crystalline structure. Yes, I have done that, but that has not resulted in any significant work that we can publish yet. But if you have something in your mind that you want to do that, on that system, then I'm more than happy to talk to you about that. And one thing that I'd like to mention is that the Chalcosin height for this iron sulfide is also significantly better in DMFT compared to DFT results. Yeah. So that much I can say. And I haven't done much after that because we were not sure what we were going to do with the calculation. So I stopped it there. But if you have something in your mind, then definitely we can collaborate on that. Thanks.
Thank you. And again, everyone, if you have any questions, you can just unmute your microphone and ask a question, whether it is for Mr. Khanal or Mr. Pandey. Please feel free to raise your question.
Hi, this is Santos.
Hi, Santos.
Okay, I have one. Okay, so most of your presentation, you talk about comparing just standard DFT with DMFT, but yeah. At first, like you had very nice talk. I really, I was really impressed with all those details. But my concern is like you always compare, almost all time you compare standard DFT, which is already known. They give us like a constant gap that's not real, so nobody does standard DFT, just PV type or LDA type to calculate nickel oxide or iron or any transition metal systems. So in your research, if you had compared using those Hubbard correction term in your calculation and compare with the DMFT, then we can see whether we need to go to DMFT or just cross U is sufficient. So can you comment on this?
Yeah, thanks, Santosh Dai. That's a very good question that you raised here. Yes, as you said correctly, I used only plain DFT or plain LDA or plain GGA results to compare with my dynamical mean field theory results. And if I, yes, in a lot of cases here, the LDA plus U term, or whenever you can have the magnetic moment or just the U term, does improve the results in a lot of systems, yes. However, that is not always the solution for in explaining the physics of the system in its entirety. What I mean is that adding the magnetic moment in the, if you remember, I mentioned it, magnetic moment in the DFT, it improves crystal structure, for example. But if you do the Fermi surface calculations or electronic structure calculation, including the band structure, those are not necessarily correct or better in when you use the magnetic moment or the static magnetic moment. And yes, in a lot of systems, if you are specifically focusing on one particular property to measure or to calculate, then it may be a good idea to go beyond LDA, just use LDA plus U. As I mentioned here, the magnetic DFT gives us better value for the Chalcogen height for both iron selenide and iron telluride, and so does in a lot of other cases. However, when you want to study these effects of the fluctuating moment, that cannot be reproduced using LDA plus U or LDA or magnetic static magnetic moment in the system, because those are still the static magnetic moment, and the effect of the fluctuating moments cannot be reproduced using the static magnetic moment. So I would say yes, you can always do GFT and DFT plus U like calculations for the case of these externally correlated systems, including NIO, and they have improved the results, yes. But if you want to do the holistic picture of these extremely correlated systems, I think the DMFT is the ultimate theory that you would like to use, which gives us physics from different perspectives and different angles, which is consistent with the experiment.
Yeah, so yeah, I agree that part. So what I was trying to say is like not all of those materials we need to go to DMFT. Within DFT or DFT plus U, I think we can have significantly accurate result. That's what I was trying to say. For example, you are showing here plus U result, but U is a parameter, so you can tune that, and then you can come, for example, you can match with the experiment, right? So
yes.
Yeah. So in that case, like I was a little bit concerned that maybe there are, of course, there must be some categories of materials we need to go to DMFT. But some systems such as iron selenide is a transition metal system, and then you can use U, have it functional, GW, and then you can get very good results already. That's
Well,
right. And
yeah, sorry, go ahead.
yeah, that's why I was thinking, like, instead of going into broad exploring within DFT, and then finding out that this is the optimized one structure and the property, and then we are picking something from DFT which is not optimized, and then comparing with DMFT, then definitely our DMFT is better, of course, with the cost of those computational resources and time. So yeah, so whole point is like, just like just like a disease, like some disease, you don't have one medicine for all diseases. So just like different materials, you have different the tools. These are tools, some have some limitations, some and then the other. So I was just curious about all your calculations. If compare with optimize plus U, whether that is who is very close with the DMFT or not, right?
Yeah, so you raised a lot of points, and I mean, you're right in most of the cases. Most of the points that you made in that DFT plus U results is it's great. It improves significantly compared to DFT. But the question that I'm asking is getting the right result or getting right result compared to the experiment, is that more important, or is because when I'm tuning this parameter, let's say U or any other parameter for that case, I mean, that is not a reliable, I mean, of course, in my opinion, that is not a reliable way to explain the physics. What if that's not the parameter that you want to tune? There may be something else going in the inside the system that we don't know yet. And for those sort of questions, we cannot just tune one or two or many parameters. For example, I've seen a paper where they have a tight binding model and they have like a lot of parameters, and if you tune all of them, and then sometimes one gives correct answer to one physical result, and sometimes the other set of parameters gives correct results to the other physical parameters. But do we want to do that, or do we want to do this holistic approach where you don't tune anything in DMFT, where you can use all the electrons, this is all electron calculations, and just let the system do whatever it wants to do, and we try to understand what's going on there, even without actually tuning any set of parameters. But having said that, you mentioned correctly that adding U gives us better result for a lot of systems. But the good question is, the question to ask here is like, do we really care that much about agreeing with the experiment, or we want to really understand the physics deeper than that?
Yeah, that's right. But what I'm trying to say is, because U is not, U is also like somewhere you are introducing strong correlation in the system, even if you are within DFT. So then, of course, for example, some high temperature superconductor or other things we cannot explain from DFT that perspective. But some systems. Some system, if we are not going to optimize randomly everything to get the accurate result, but within that physics, we have also some physics within plus U as well. For example, nowadays people are using U in oxygen, other pieces, orbitals, and so on to match the experiment. I'm not talking about that.
Once again, why do you do that? Because we know from our understanding of physics that there is no U in oxygen, right? It's p orbital.
Yeah, that's what I'm saying. I'm not trying to do that random things, but within physics, we can do for the transition metal system. That's like constant interaction, Coulomb interaction. You can calculate actually, so it's not kind of random. So you can calculate what they do, and then but what I think is most of the SIP system, if it is not very complicated, it should be close enough with the DMFT. Yeah.
So let's move on to other questions, and we can discuss more sometime. I would be happy to. I would really be happy to talk to you more about this.
Okay. Thanks.
Yeah. Any other questions? Sure. Thanks for the questions.
Ghanshyamji, this is Shambhu. Thank you. You already answered my question about band structure. I just wanted to mention that this link I forwarded in the chat is about an experiment that we done nickel oxide,
Okay.
which you mentioned right as a standard strongly correlated electron systems, and here we wanted to see ultra fast modification of the band structure.
Okay.
When this material is subjected to strong ultra fast laser field, how does the band structure evolve? So we don't really have a full theory, although you can see some theoreticians that you may know in the author list, and you may want to check the paper.
Oh, that would be really good. Thank you so much, Samurai. I will definitely check. Yeah.
Thanks for the nice talk.
Thank you.
Yes. Any more question? All right. So
yeah,
I would wait for like 30 seconds if you have any question for Mr. Khanal or Mr. Pandey. Yeah, looks you guys have made everything clear for everyone.
Or everything not clear for everyone.
Anyway,
okay.
I would like to thank once again to both the speakers, Mr. Pandey and Mr. Khanal, not only for today's presentation, for so many they have been helping and participating and in all the NPAS activities from the beginning and supporting very in each and every activities of NPAS. So I would like to thank you for that also. And at the same time, I would like to thank all of you guys for joining us. So keep following NPAS Facebook page, web page, YouTube channel, and we'll have next talk on October 18th at 9 p.m. Eastern. So for now, thank you everyone again and have a good night. See you.
Thank you. Thank you.